Hello everyone, welcome to PW Gulf. So today is the time for the ultimate recap session of the chapter Units and Dimensions. We have studied this chapter in our lectures class with complete detail, studying each and every topic in full energy and complete depth. Now, so today is the time for its recap. Today we will revise all our topic in one complete session. So let's start our session with energy and confidence. So first we'll be talking about fundamental forces and the conservation laws. What basic four fundamental forces exist in nature and the conservation laws. Then we will be dealing with physical quantities and system of units. What are physical quantities, how we measure them, in which two categories they are divided. Then we'll be talking about units, system of units we use. Then we'll do dimensional analysis. What are the dimensions of a physical quantity, principle of homogeneity, and how dimensions are helpful in checking the correctness of a equation, deriving relationships, etc. Then we'll be moving on to errors. Okay, error analysis will be the last topic of the day. So let's start our today's session. So first is fundamental forces in nature. So what are the fundamental forces in nature? There are four fundamental forces in nature. Number one, gravitational force. Number two, electromagnetic force. Then comes the strong nuclear force. Then comes the weak nuclear force. So we have four fundamental forces in our nature. Let's study them one by one. Gravitational force. So the force which acts between the two masses by virtue of their mass is called gravitational force. Let us take, we have two bodies, one of mass m1 and the other body is of mass m2. The distance between their centers is r. Okay, the distance between their centers is r. Then gravitational force acting between the two bodies will be equal to g m1 m2 by r square. This result we get from Newton's laws of motion. This result we get from Newton's laws of motion, that the force acting between two bodies m1 and m2 who are separated by a distance r from the centers is f is equal to g m1 m2 by r square. So from here we can see that the force is inversely proportional to the distance and force is directly proportional to the product of the masses. So force is inversely proportional to r square and directly proportional to m1 into m2. The force which acts between the two bodies by virtue of their masses is called the gravitational force. Let us study its properties. Gravitational force is always attractive in nature. It is always an attractive force. It is never repulsive. Then it obeys inverse square law. What is our inverse square law? That force is proportional to 1 by r square. This is our inverse square law, that our F is directly proportional to 1 by r square. It is a long range force. Okay, it is a long range force. When will gravitational force become zero? When the distance between two bodies is infinitely large, then it will become zero. So it is a long range force, does not need any intervening medium for its operation. Okay, if there is vacuum or there is medium, air, water, oil, any medium, gravitational force will always act between two masses. It doesn't need any medium for its operation. The gravitational force between two bodies does not depend upon the presence of other bodies. Okay, see what this line means to say. If I have two bodies m1 and m2, there will be a gravitational force acting between them. Now I place another third body, there will also be a gravitational force acting between them, but this force will remain the same. So gravitational force doesn't depend upon the presence or absence of other bodies. It is the weakest force known in nature. It is the weakest. All other forces are stronger than gravitational force. It is a central force and it is also a conservative force. What is a central force? Which acts along the line joining centers of two particles. So gravitational is a central force. It is also a conservative force. Okay. What are conservative forces? The forces under which work done against them is not dependent upon the path being followed. It is independent of the path followed, only depends on the initial and final position are called the conservative forces. So this is all about gravitational force. Next comes our electromagnetic force. What is electromagnetic force? The force which acts between two charges or two magnetic poles. Okay, if we have two charges at rest, then the force is called electrostatic, and if we have two magnetic poles, then the force is called magnetic force. Now why we combine them? Because a changing electric field can produce a magnetic field, and a changing magnetic field can produce an electric field. That's why we study these forces in a combined way, electromagnetic force. Suppose we have two charges Q1 and Q2 which are placed r distance apart, okay, which are placed r distance apart. So the electrostatic force between them will be equal to k q1 q2 divided by r square. So this force is also proportional to 1 by r square. This is our electrostatic force. It is also proportional to 1 by r square. So what are properties? It can be attractive or repulsive. If we have two like charges, the force will be repulsive. If we have unlike charges, the force will be attractive. Similarly, if we have like poles, the force will be repulsive. But if we have unlike magnetic poles, the force will be attractive. So it can be attractive as well as repulsive in nature. It also obeys inverse square law. We just saw F is proportional to 1 by r square. It is a long range force and doesn't need any intervening medium for its operation. It also doesn't need any intervening medium if there is a medium or there is a vacuum. Gravitational as well as electromagnetic forces will act over there, okay? Then it is 10 raised to the power 36 times stronger than gravitational force. So F electrostatic or electromagnetic is 10 raised to the power 36 times stronger than gravitational force. It is also a central force. It is also a conservative force. Okay, it is also a central force. It is also a conservative force. These are all the properties of electromagnetic force. See next force, that is strong nuclear force. Now in our nucleus we have protons and neutrons. So protons and protons are like charges. They must repel each other. Okay, they must repel each other. How come then the nucleus is a stable? How come then the nucleus is stable? There must be a force which binds the nucleus together and which must be stronger than the electrostatic repulsion between the protons. Then only we can hold the things together. Proton are both positively charged. They will repel each other. Then how can they sit closely in a nucleus? So there is a force which binds together the protons and the neutrons in a nucleus, and that force is called a strong nuclear force. So what are the properties? It is basically an attractive force because it binds the particles together, but it becomes repulsive when the distance between the nucleons is less than 0.5 Fermi meter. Okay, it becomes repulsive when the distance between the nucleons is less than 0.5 Fermi meter. It is a very short range force because it acts only over the size of nucleus. So basically the work of strong nuclear forces to bind the protons and neutrons together in a nucleus. It has only purpose is to bind all the protons and neutrons together in a nucleus. So it is a short range force, acts only over the size of nucleus. Now it is 10 raised to the power 38 times. Okay, so strong nuclear force is equal to 10 raised to the power 38 times stronger than gravitational force. It is 10 raised to the power 38 times stronger than gravitational force. It is a non-conservative force. It is a non-central force. Okay, it is a non-central force. It is a non-conservative force. Neither it is conservative nor it is central. It is a charge independent force. What do we mean by charge independent? It doesn't depend upon the charge of the nucleons. So that's why the force between two protons will be equal to the force between two neutrons will be equal to the force between a proton and a neutron. It does not depend upon the charge of nucleon, whether my nucleon is charged or chargeless. It is independent. The strong nuclear force between two protons is equal to the strong nuclear force between a proton and a neutron, and also equal to the strong nuclear force between two neutrons. So this is a strong nuclear force. Let's come to weak nuclear force. What is weak nuclear force? In beta decay of a nucleus, we get particles such as neutrinos or antineutrinos. Now these are elementary particles. You will study about these elementary particles in the higher classes. You don't know about them today, but you will get to know them when you will study nuclear physics. So in beta decay, we do get some elementary particles which interact only via weak nuclear force. Okay, these are leptons. These are chargeless particles. They do not interact by strong nuclear interaction. They interact via weak nuclear force. That's where weak nuclear force comes into picture. It is the force that appears only between elementary particles involved in a nuclear process such as the beta decay of the nucleus. Okay, it is only present where we have a nuclear process in which we get neutrino or antineutrino, because these particles only interact via weak nuclear force. So let us study its properties. Any process involving neutrino and antineutrino, any process in which we get a neutrino or antineutrino, is governed by weak nuclear force, because these particles can experience only weak interactions. These particles cannot experience other forces. They can only experience weak interactions. So they interact via weak nuclear force. It is also a short range force. It only acts over the size of nucleus. Now it is 10 raised to the power 25 times stronger than gravitational force. So weak nuclear force is 10 raised to the power 25 times stronger than gravitational force, and it is only present when we have the particles antineutrinos and neutrinos. When we have these particles in any nuclear process, then we have the weak nuclear force. Okay, now let's summarize their order. So first gravitational, then we have weak nuclear, then we have electromagnetic, then we have strong nuclear force, or simply Fn. So the order will be 1 ratio 10 raised to the power 25 ratio 10 raised to the power 36 ratio 10 raised to the power 38. Okay, so this will be the ratio of gravitational force to weak nuclear force to electromagnetic force to strong nuclear force. If we arrange them in order, so gravitational force is the weakest, then we have the weak nuclear one, then we have the electrostatic, and then we have the strong nuclear force. Okay, so now let's move to conservation laws. So there are 4 laws of conservation. Let us study one by one. What does the first conservation law say? That first law is conservation of energy. So whenever any process occurs, okay, whenever any mechanical process occurs in a physics, then some quantities change with time. Suppose a body is moving on a road, so its velocity may be changing or may not be changing. Its displacement is changing with time. So there are some quantities that change with time, but there are simultaneously some quantities which do not change with time, okay, and that quantities are called conserved quantities, and the laws which govern them are called conservation laws. So first come is the law of conservation of energy. Let's study what this law states. That law of conservation of energy states that energy can neither be created nor be destroyed. It can only be transferred from one form to another. Energy can neither be created nor destroyed, but it can be changed from one form to another. Or equivalently, we can say that the total energy of an isolated system remains constant. Okay. What does the law of conservation of energy says? That energy can neither be created nor be destroyed. We can only convert it from one form to another. Okay. Just let us see an example. As soon as we switch on the light, we have electrical energy in the wires, which get converts into light energy in the bulb, and then this light energy heats up the environment and bulb and gets converted into heat energy. So we have energy converting from one form to another. And let us say we are operating a toy which is having a battery inside it. So battery is having chemical energy which is converted into electrical energy in the circuit when we operate, switch on the toy, and then the toy, whatever work the toy is doing, it is converted into mechanical energy. Suppose it is fan rotating or an arm moving of any toy, then it is converting into mechanical energy. So energy can be converted from one form to another, but neither we can create it nor we can destroy it. Next comes the law of conservation of linear momentum. What is linear momentum? P is equal to mv. We have studied this. So linear momentum, what is the law of conservation of linear momentum? If net external force acting on a system is 0, okay, if no external force acts on the system, then its linear momentum remains conserved, or its linear momentum is constant. Okay, what does this law says? That if F net on a system, net external force on a system is 0, then the momentum is constant. Okay, then the momentum remains constant. This is the law of conservation of linear momentum. Let's study the third law. Third law states that if it is the law of conservation of angular momentum. So linear momentum we have in a linear motion in a plane when a body is moving in a line or along any curve. But when a body is rotating along the axis, okay, rotating with respect to some axis, then we have angular momentum. So what does law of conservation of angular momentum says? That it states that if no external torque acts on the system, if no external torque acts on the system, then its angular momentum is conserved or it remains constant. That is, if tau net torque is 0, tau net is equal to 0, then angular momentum is equal to constant. Okay, if angular tau is 0, then angular momentum will be constant. This is the law of conservation of angular momentum. Now next comes the law of conservation of charge. Just like energy, if we have an isolated system, neither we can create charge nor we can destroy charge. Charge can be transferred from one body to another, but it cannot be created, it cannot be destroyed. If we have an isolated system, its total charge always remains constant. Okay, it states that total charge of an isolated system remains constant. This implies that electric charges can neither be created nor be destroyed. They can only be transferred from one body to another. This is the law of conservation of electric charges. So these are the four laws of conservation: law of conservation of energy, law of conservation of linear momentum, law of conservation of angular momentum, and law of conservation of electric charge. So this is all about electric fundamental forces and laws of conservation. Now, next topic, what we have in this chapter is physical quantities. What are physical quantities? Okay, till now we have encountered many physical quantities like length, mass, we measure time, weight, force, velocity, acceleration, displacement. We encounter numerous physical quantities in our daily life. So what are physical quantities? All those quantities which can be measured either directly or indirectly. So any quantity we have, there are two methods to measure it. One is the direct method, just like length, we can measure the length directly, or mass, we can measure it mass directly. Time, we can measure the time directly, or indirectly we cannot measure the velocity directly. We need to calculate displacement and time simultaneously so that we get the velocity of the body. So this is how we can do direct or indirect measurements. So all those quantities which can be measured either directly or indirectly are called physical quantities. And in terms of these physical quantities, all the laws of physics are defined. Okay, so what are physical quantities which can be measured directly or indirectly, and in terms of which the laws of physics are expressed, are called physical quantities, Now these physical quantities are of two types. We have divided these physical quantities into two types. One is the fundamental quantities and next is the derived quantities. Okay, first part is the fundamental quantities. Now what are fundamental quantities? These are the basic quantities. Okay, these are the basic quantities, or those quantities which cannot be expressed in terms of other quantities. Those quantities which can't be expressed in terms of other quantities, these are independent of the other quantities. Okay, those quantities which are independent of the other quantities are called fundamental quantities. Let's take their example. Mass, we cannot express mass in terms of other quantities. Then length, then time, etc. All these are my fundamental quantities. Next category is of derived quantities. So what are derived quantities? All those quantities which are dependent on fundamental quantities. Okay, all those quantities which are dependent on fundamental quantities or can be expressed in terms of fundamental quantities are called derived quantities. We can derive these quantities out of the fundamental quantities. Example of these will be velocity, acceleration. So velocity is displacement by time, length by time. Length and time both are fundamental quantities. Acceleration, velocity by time. Then we have force. Then we have energy, power, etc. All these are derived quantities. We derive these quantities out of the fundamental quantities using some or the other relations. So we have two types of physical quantities. One is fundamental and other is derived. Now come how we measure these fundamental quantities. How can we measure any quantity or a fundamental quantity? Suppose you have to measure a rod, length of the rod. Okay, I gave you a rod of L length and I asked you to measure it. Okay, I asked you to measure it. You will say that, ma'am, please provide a scale to measure it. Yes or no? You will say that, ma'am, please provide a scale to measure it. So I provided a 1 centimeter scale and I provided a 1 meter scale. Okay, I provided two scales to two different students. To one student I gave a 1 centimeter scale and the other student I gave a meter scale. Now what the students will do? Students will compare the length of this rod. They will keep the scale besides the length of this rod and check how many repetitions of the scale are needed to measure the length of the rod. Yes or no? They will check how many repetitions of the scale are needed to cover the length of this rod. So this is how we measure. What is the process of measurement? This is the only process of measurement when we compare our given quantity with a fixed value, a standard value of the same quantity. Okay, fixed standard value of the same quantity. This process is called measurement. So measurement of a physical quantity is the process of comparing this quantity with the standard amount of same physical quantity. This is measurement and that standard amount is called unit. Okay, and that standard amount is called unit. So this centimeter scale is the unit which we are using to measure the length of this rod. This meter is the unit we are using to measure the length of this rod. Now see, when my first student measured the length of this rod, he tells me that it is 130 centimeter long. Okay, he tells me that it is 130 centimeter long and the second students tell me it is 1.3 meters long. Okay, first tells me 130 centimeters, second tells me 1.3 meters. Now what does this 130 centimeter tells me? It is telling me how many repetitions of the scale were needed to cover the length of the rod. So this 130 is called the numerical value. Okay, this 130 is called the numerical value and this centimeter is the standard reference value we use to measure it. This is called the unit. Okay, this is called the unit. So 130 is the numerical value of the length in centimeter unit. Okay, 130 is the numerical value of the length of the rod in which unit? Centimeter unit. Then in meter unit, this meter will be my unit I used, reference, some standard amount I used to measure it, and this 1.3, this is the numerical value. Okay, this is the numerical value in which unit? This is the numerical value in which unit? Meter unit. Okay, this is the numerical value in meter unit. So after the measurement process, we get two things. One is the numerical value and the other is the unit. Okay, so how we represent a quantity? How we represent a quantity? A quantity can be represented by numerical value multiplied by unit which is being used. Okay, so how we represent the quantity? We represent the quantity as numerical value times the unit. So if my quantity is Q, then we can write it as N is the numerical value, U is my unit, so Q is equal to NU. Okay, Q is equal to NU. Now in the previous example, L is equal to 130 centimeter and L is equal to 1.3 meters. Both are the length of the same rod, so they must be equal. So they must be equal. So if we have N1 is the numerical value in unit U1. Okay, if we have N1, Suppose we are measuring some Q quantity using unit U1 and the numerical value came out to be N1. N1 is the numerical value in unit U1 and N2 is the numerical value. It is the numerical value in unit U2. It is the numerical value in unit U2. Then I can write my quantity Q will be equal to N1 times U1. And from here I can write Q is equal to N2 into U2. Because these are the measurement of the same quantity, so Q quantity must remain same. So N1 U1 must be equal to N2 U2. Okay, N1 U1 must be equal to N2 U2, or we can say that numerical value is inversely proportional to the unit being used. Okay, N1 U1 is equal to N2 U2, or we can say that numerical value is inversely proportional to the unit being used. See, larger the unit, smaller is the value. Meter is a larger unit, 1.3 is smaller. Centimeter is smaller unit, we get the numerical value 130. Smaller is the unit, larger is the numerical value, or larger is the unit, smaller is my numerical value. Okay, so this is all about the measurement process. Now, which unit we should choose for measurement? The unit chosen should be very suitable, it should be easily available, it should be constant with time, it should be easily reproducible so that we can make numerous copies of it, it should be well defined. So these are all the desirable quantities that a unit must have. Now let us talk about system of units. So we make a different systems of unit. We make a set. Okay, we make a set of units that in the first set these fundamental quantities will be measured in this unit. In this set these fundamental quantities will be measured in this unit, so that we can get a uniformity. If I'm using some system of units, then I have to represent all the quantities using that units only. So there are basically four fundamental, four system of units which are commonly being used. The first one is FPS, second one is CGS, third one is MKS, and fourth one is SI system. So these are the four most commonly used system of units. FPS was used by Britishers. This is an English system, not used in our countries these days. Out of these, the most acceptable and widely used all over the world is the SI system of units. Now let us study the system of units one by one. So in FPS, MKS and CGS, we define the units of only three fundamental quantities: length, mass and time. Okay, length, mass and time, we only define the units of these fundamental quantities. In FPS system, we use length in foot. Okay, foot is the unit used to measure length, pound is the unit used to measure mass, and second is the unit used to measure time. In FPS, we have foot for length, pound for mass, second for time. That's why the name FPS, foot, pound and second. Okay, that's why the name FPS, foot, pound and second. In CGS, we use centimeter to measure the length, gram to measure the mass, and second to measure the time. That's why the name CGS, centimeter, gram, second. Okay, centimeter, gram, second, CGS. Next comes the MKS system. MKS, we use meter for length, kilogram for mass and time in seconds. That's from where the name gets MKS. Okay, MKS. So for FPS, foot, pound, second, CGS, centimeter, gram, second, MKS, meter, then we have kilogram, and then we have second. Okay, meter, kilogram and second, these are the units used in MKS. So Now comes only one system which is left, that is SI system. How SI system is different from the MKS system? SI system is a better version or a modified version of MK system. MK system, we defined only three fundamental quantities: length, mass and time. But in SI system, we have seven fundamental quantities and two supplementary quantities. Okay. According to SI system, there are seven fundamental quantities and two supplementary quantities, and any number of derived quantities we can make out of these quantities. Okay, so SI system is a modified version of MKS system. In SI system we have seven fundamental quantities. What are these? First is the length, second is mass, third is time, fourth is temperature, next is the electric current, then the luminous intensity, and seventh is the amount of substance. So we have seven fundamental quantities: length, mass, time, temperature, electric current, luminous intensity and amount of substance. Now let us see what their units are. Length is measured in meters, mass is measured in kilograms, time is measured in seconds, temperature is measured in Kelvin, electric current is measured in amperes, then luminous intensity in candela, and amount of substance is in moles. Okay, so these are the units which are used to measure the seven fundamental quantities. We have meter, kilogram, second, Kelvin, ampere, candela and mole. These are their symbols. Okay, these are their symbols. So these are our seven fundamental quantities. Okay, these are the seven fundamental quantities and their units in SI system. So SI system is the internationally acceptable system, most widely used system these days. Now let us study the supplementary quantities. So what are supplementary quantities? There are two supplementary quantities: plane angle and solid angle. Okay, plane angle and solid angle. What is a plane angle? The angle subtended by an arc of the circle at the center in the plane of the circle is plane angle, and the angle subtended by an area, okay, by an area of the sphere at the center is called solid angle. What are the units? We use radians for plane angle and steradians for solid angle. Okay, we use radians for plane angle and steradian for solid angle. So these are the supplementary quantities. Now just like we have a fundamental quantities and derived quantities, similarly units are also divided into two categories: fundamental units and derived units. Okay, fundamental units, and then we have the derived units. The units which are used to express fundamental quantities are called fundamental units. Use the units of fundamental quantities. Example is meters, kilogram, second, etc. These are the fundamental units, and all the units that can be derived from fundamental units are called derived units, or all the units which are used to measure derived quantities are called derived units. Example is meter per second square, Newton, joule, watt, etc. All these are derived units. Okay, so this is all about quantities and units. Okay, what physical quantities are, how we measure them, what are the system of units which are being used to measure them, and how we divided units into two categories. Now next comes is the dimensional analysis. Dimensional analysis. What are the dimensions of a physical quantity? Okay, what are the dimensions? Suppose we want to express area. Suppose we want to express area. So area will be length multiplied by length. If we have square, it is a square. If we have rectangle, it is L into B. If we have triangle, it is half into base into height. So it will always have length multiplied by length. Now, what are the dimensions of physical quantities? Can I write area as length square? Can I write area as length square? So the dimensions of physical quantities are the powers or exponents, to which fundamental quantities must be raised to represent that quantity. So the power or exponent to which this fundamental quantity must be raised to express this quantity is called dimensions of that quantity. So dimensions of area is length square. Okay, dimensions of area is length square. We have, if we write dimensions of length as L, okay, we write dimensions of length as L. We need to raise L to the power 1 to get a length, and similarly, if we have to write dimensions of mass, we write it as M, and time, we write it as capital T. Then temperature, we write it as capital K. Electric current, we write it as capital A. Similarly, luminous intensity as CD and amount of substance as mole. So this is how we represent. Now if we want to represent any quantity x, then I have to express the x in terms of these fundamental quantities, and to what power or exponent these fundamental quantities must be raised to get x are called the dimensions of x. Now what is dimensional formula? The expression which shows how and which fundamental quantity must be needed to represent that physical quantity is called the dimensional formula of that physical quantity. Suppose we have x, a quantity whose dimensions are m raised to the power a, l to the power b, and t raised to the power c. So this expression is called the dimensional formula. And when we equate this dimensional formula to that quantity, this whole expression, that x is equal to m raised to the power a, l raised to the power b, and t raised to the power c, this whole expression is called dimensional equation. Okay, this whole expression is called dimensional equation. And these exponents or powers a, b, c, to what power I should raise m, or to what power I should raise l to get x, is called the dimensions of x. Okay, this is called the dimensions of x. Now how and where we use these dimensional analysis, we will study. Now comes the principle of homogeneity. What does the principle of homogeneity says? Now tell me one thing, can I add 5 kg to 2 meters? Can I add 5 kg to 2 meters? I have given you 5 kg of rice. Please add 2 meters of cloth to this. Can you add it? Can you add it? No. But if I give you 5 kg of rice and I ask you to add 2 kg of sugar to it, you can add it. You will add it and you will say that this combination of mixture is of 7 kgs. Okay, this combination of mixture is of 7 kgs. But if I tell you to add 2 seconds to 3 meters, can you add it? I ask you to add, please add 2 seconds to 3 meter. We cannot add it. Okay, we cannot add it. So whom we can add and whom we can subtract. Similarly, Just please subtract 5 kgs from 8 meters. No, we can't subtract it. But can we add 2-meter cloth and again a 3-meter cloth? Yes, we will get a 5 meter of cloth. Okay. So length can only be added with length. Mass can only be added with mass. Time can only be added with time. Only similar quantities can be added or subtracted. Only similar quantities can be added or subtracted. Then we have 3 meters is equal to 5 liters. Okay. 3 meters is equal to 5 liters. Are this equation? Is this equation correct? Can 3 meters be equal to 5 liters? No. 3 meters will only be equal to 3 meters. If I say you 6 Newton of force is equal to 2 seconds, how can a force be equal to time? No. Only force can only be equal to force. This is what principle of homogeneity says, that principle of homogeneity says that the dimensions on the right hand side of a equation must be equal to the dimensions on the left hand side of a equation, and only dimensionally same quantities can be added or subtracted from each other. So let us see, according to this principle, a physical equation will be dimensionally correct if the dimensions of all the terms occurring on both sides of the equation are same. Okay, dimensions of all the terms occurring on both sides of equation are same. This is based on the principle that only the physical quantities of the same kind, can be added, subtracted or compared. Clear? So what we have is dimensions on left hand side must be equal to dimensions on right hand side. Okay, dimensions on left hand side must be equal to dimensions on right hand side. Only same dimensionally same quantities can be added or subtracted. Okay, dimensionally same quantities can be added or subtracted or compared. Okay, add, subtract or compare. So this is what principle of homogeneity tells us. The dimensions on both sides of the equation must be same and only similar quantities can be added or subtracted from each other. Now let us study the application of these dimensional analysis. So dimensional analysis can be used to check the correctness of any physical equation which is given to us. Suppose we are given S is equal to ut plus half a t square. Okay, suppose we are given this equation, S is equal to ut plus half a t square. Now this equation will be dimensionally correct if the dimensions on the left hand side are equal to the dimensions on the right hand side. If the dimensions are different, then equation is wrong. We cannot have any equation in which left hand side is having different dimensions and right hand side is having different dimensions. So let us check. S is my displacement. Let us check for left hand side. S is my displacement. So displacement will have the dimensions of length. Displacement will have the dimensions of length. Now let us check for right hand side. Now for right hand side, first is ut. Let us check the dimensions of ut. Dimensions of ut will be dimensions of u into dimensions of t. What is my u? U is my initial velocity. So velocity will have the dimensions of displacement per unit length. So lt minus 1 into t. Lt minus 1 into t, that will come out to be L only. So ut is having the dimensions of length. Then the next quantity we have is half a t square. Okay, what will be dimensions of half? Is a dimensionless number. Dimensions of a into dimensions of t square. So what are dimensions of a? Acceleration, velocity per unit time. So L t minus 2 into t square will be time square. Now multiply it, we will get L. So ut and half at square both have same dimensions, L and L. So we can add them. Yes, we can add them. Okay. Yes, we can add them. We can only add quantities having same dimensions. So ut can be added to half at square. First point is checked. Then dimensions of the left hand side are L. Dimension on the right hand side, all quantities on the right hand side are having the dimensions of L. All the terms like ut, half at square, both the terms are having the dimensions of length and length. So when we add length to length, we will get a length only. So this equation is dimensionally correct. Okay. So the dimensions of left hand side are equal to dimensions on the right hand side. So this equation is dimensionally correct. This equation is dimensionally correct. So this is how we can check the correctness of a given physical equation. We can also use the dimensional analysis method to derive a result between the relation between different physical quantities. Let us take an example. Now we are given that kinetic energy depends on mass, speed and time. Okay. We were given the expression that kinetic energy of a body is depending upon its mass, speed and time. But we don't know how this kinetic energy is dependent upon mass, whether it is directly proportional to mass, inversely proportional to mass, directly proportional to mass square, inversely proportional to mass square or any other. We don't know how this is dependent. We just know that it is dependent upon mass, speed and time. Now we want to derive a relation between this kinetic energy, mass, speed and time. We want to know how exactly it is dependent. So let us take that kinetic energy is directly proportional to m raised to the power a, speed raised to the power b and time raised to the power c. Okay, let us take that energy is directly proportional to m raised to the power a, speed raised to the power b and time raised to the power c. Now if we remove this proportionality sign, we will add a constant m raised to the power a, v raised to the power b and t raised to the power c, where k is a dimensionless constant. Okay, k is a dimensionless constant. K is not having any dimension. Okay, k is not having any dimensions. Now if we get to know the values of a, b and c, then we can know that whether it is inversely proportional, directly proportional, we will get the relation. Now apply the principle of homogeneity. Dimensions on the left hand side of the equation must be equal to dimensions on the right hand side of the equation. So what are dimensions of energy? ml to t minus 2. Okay, ml to t minus 2. What are dimensions of mass? So it will be m raised to the power a, velocity lt minus 1 raised to the power b and time t raised to the power c. Dimensions of m raised to the power a will be m raised to the power a, v raised to the power b will be lt minus 1 raised to the power b and t raised to the power c. Now combine them. So this will become m raised to the power a, l raised to the power b and t raised to the power minus b and t raised to the power c. Now see, base same, they are in multiplication, powers will get added. So what we will get is m raised to the power a, l raised to the power b, t raised to the power minus b plus c. Okay, this is what we get from this equation, that energy is equal to, on left hand side we have ml2 t minus 2. This is equal to m raised to the power a, l raised to the power b, t raised to the power minus b plus c. Okay, now dimensions on the right hand side must be equal to dimensions on the left hand side. Comparing both sides, so a must be equal to 1 because dimensions on left hand side should be equal to right hand side. B should be equal to 2 and minus b plus c should be equal to minus 2. Substitute the value of b, minus 2 plus c is equal to minus 2. From here we will get c is equal to 0. So when we compare the values, we get the values of a, b, c as 1, 2 and 0. So what was our relation with energy? Energy is equal to k times m raised to the power a, m raised to the power 1, b raised to the power b, b raised to the power 2 and t raised to the power c. So t raised to the power 0. So we will get the expression of energy as kmv square. Okay, we will get the expression for the energy as kmv square. So we only knew that energy, kinetic energy, depends upon mass, velocity, speed and time. We get a relation using dimensional analysis between the various quantities. So k is equal to mv square. Now we know that energy is directly proportional to mass and directly proportional to square of velocity. This is where we use dimensional analysis. Let's move forward to limitations of dimensional analysis. There are limitations of this method. What are the limitations? This method doesn't give any information about the dimensionless constant k. We don't know the value of k using this method. It fails when the physical quantity depends upon more than 3 quantities. Okay, when physical quantities depends upon more than 3, it fails there. And when we have equation in the form of sum or difference of more than 2 quantities, just like S is equal to ut plus half at square, such equations cannot be derived because we always assume the equation to be in multiplication. See, we assumed E is equal to K m raised to the power m multiplied by V multiplied by T. So these equations having sum or difference of more than 2 terms, more than 1 term, we cannot calculate them. Okay, relationships having trigonometric ratio, logarithmic ratio, exponential, all these are dimensionless, so we cannot derive them. Okay, we cannot derive them. Sometimes it is also difficult to identify the factors on which physical quantity depends because some relations have dimensional constants. Okay, just like G, H, gravitational constant, Planck's constant, or permeability, permittivity, all these are dimensional constants. So whenever equation have more these dimensional constants, so this method becomes complicated. We can only use it there where we have dimensionless constant. So these are the limitations of dimensional analysis. This is all about dimensional analysis. Let us move to significant figures. So what are significant figures? Let us study the significant figures through an example. We want to measure the length of the rod, but to measure the length of the rod, we have 3 scales. Okay, we have 3 scales. One scale is having a least count of 0.1 meter, other is having a least count of 0.01 meter, and the third one is having a least count of 0.001 meter. When I measured my length using the first scale, I get length is equal to 2.3 meters. Okay, I got length is equal to 2.3 meters. When I measured it using second scale, I get the length is 2.28 meters. And when I measured it using third scale, I got to know that length is 2.283 meters. So what is happening over here? When we place the rod and the scale, okay, when we place the rod and the scale, if here is my 2.3 mark, here is my 2.4 mark, I am not able to measure this distance because my scale is only having a mark of 2.3 and 2.4. I am not able to measure this distance. So what we are measuring is approximate value. We are confident of this measurement only up to this digit. This can be different because we don't know the exact measurement. Okay, if we have a better scale, we could measure that distance also. When we used a better scale, we found that it is 2.28. Now in this we are confident about 2.2, but we are not confident about this 8. If we have a more precise scale, we could have know that it is either 2.278 or it is 2.271, 2.27, like this. So whenever the precision of our scale is changing, we are getting measurements different because in every measurement we have some quantities, some digits which we are very sure about. Okay, very sure about, like this 2, 2.2, 2.28. We are very much sure about these units, but we are not sure about this last digit. We are uncertain about this digit. If we have a better scale, this digit could change. So what are significant figures? Significant figure is the total number of digits that are known with full confidence plus the first uncertain digit in any measurement gives us the significant figure. So what are significant figures? Number of digits number of digits known with surety or full certainty. Number of digits that are known with certainty plus the first uncertain digit. Okay, plus the first uncertain digit gives us the number of significant digits in that measurement. What are significant figures? Digits that are known with full confidence plus the first uncertain digit gives us the significant figures. Now how many significant figures in this number? This is confident one, this is the first uncertain, so it will have 2 significant figures. This number will have 3 significant figures. This number will have 4 significant figures. Okay, this number will have 4 significant figure. More the number of significant figure, more precise is our measurement. Now there are some set rules by which we can measure how many significant digits or significant figures are present in any number. Let us study these rules. All the non-zero digits in a number are significant. Okay, all the non-zero digits in a number are significant. So example is, if number is 234, it will have 3 significant figures. Okay, all the non-zero digits which are not equal to 0 are significant digits. Next is, all the zeros between 2 non-zero digits are significant. All the zeros that come between 2 non-zero are significant, no matter if the number is having a decimal or not having a decimal, or whether the decimal is placed before or after the zeros. It doesn't matter, no matter where the decimal point is, if at all. Example is 30.004. This number will have 1, 2, 3, 4, 5. It will have 5 significant figures. 3 and 4 are significant because they are non-zero, and all the zeros that come between two non-zero are significant. That's why all three zeros are significant. Next is all zeros to the right of a non-zero digit. Whose right? Right side of the non-zero digit, but left of a decimal point are significant. Okay, all the zeros that lie on the right side of a non-zero digit, like 7, 0, 0, decimal. All the zeros that are on the right side of the non-zero. If we, this is my non-zero, right to this non-zero and left to this decimal, all the zeros that will come between these two are significant. So this will have three significant figures. Okay, these zeros are significant. These will have three significant figures. See next rule. The trailing zeros in a number with a decimal point are significant. What are trailing zeros? The zeros that come in the last of a number, end of a number. Like if we have 68,000, these are the trailing zeros. If we have 6.800000, these are my trailing zeros. The zeros that come in the end of a number, last of a number, are called trailing zeros. Okay, these are called trailing zeros. Now, trailing zeros are significant if the number is having a decimal point. Okay, if the number is having a decimal point, then only trailing zeros are significant, like 6.300. It will have four significant figures. It will have four significant figures. Now, next is if my number is less than 1. If my number is less than 1, then the zeros on the right of the decimal point, okay, zeros on the right side of the decimal but left side of the first non-zero digit are not significant. Okay, the zeros to the right side of the decimal, if this is my decimal point, right of this decimal but left of this first non-zero digit, all the zeros that will come between are not significant. Okay, these are not significant. Example is 0.0023. So it will only have two significant figures. It will only have two significant figures, 2 and 3. These zeros are not significant. Next, the terminal or trailing zeros in a number without a decimal. So the terminal or zeros in a number without a decimal point are not significant. So for terminal zeros, we have two rules. If my number is having a decimal point, then the zeros are significant. If my number is not having a decimal point, then the zeros are not significant. Example is 63,000. It will only have two significant figures. No decimal, zeros are not significant. Decimal is present, zeros are significant. Okay, this is the rule for terminal zeros or trailing zeros. Next rule is the number of significant figure doesn't depend upon the system of units we are choosing. Whether we are doing measurement in meters, centimeters, kilometers, millimeters, the number of significant figures won't change. Suppose if we have 3.8 meters. How many significant figures? Two significant figures. Convert it into centimeter, 380 centimeters. Again, two significant figures. Convert it into millimeters. Again, 3,800 millimeters. Again, two significant figures. Okay, so if my number is expressed in different units, the number of significant figures doesn't change. So significant figures are independent of the system of units we are have chosen to do the measurement. So this is all about significant figures. Now let us see number of significant figures. A rounding off, we have to round off the number, like round off this number measurement to 3 decimal place, round off this number to 4 significant figures. So whenever we round off a number, what are the rules? Okay, If the digit to be dropped is smaller than 5, then the preceding digit is left unchanged. Suppose we have a number 2.831. I told you to round off this number, round off to three significant figures. Okay, round off this number to three significant figures. It means the final number should have only three significant figures. So which number is being dropped? 1 is to be dropped. 283 are the three significant figures. Round off this number to three significant figures. If the number to be dropped is smaller than 5, so 1 is the number being here dropped. Is it smaller than 5? Then the preceding digit before it will be remained unchanged. So we will write it as 2.83 only. Okay, we will write it as 2.83 only. If the digit to be dropped is greater than 5, then the preceding digit is increased by 1. It is increased by 1. Suppose if the value was 2.838 and I asked it to round off up to three significant figures. Again, the digit to be dropped is 8. Okay, the digit to be dropped is 8. So 8 is greater than 5. So this number will increase by 1. It will become 2.84. Okay, it will become 2.84. Next rule is, if the digit to be dropped is 5, okay, the digit we are being dropped is 5, then the preceding digit is left unchanged if it is even. Okay, preceding digit will be left unchanged if it is even. And if the digit to be dropped is 5, then the preceding digit is increased by 1 if it is odd. We will increase the preceding digit by 1 if it is odd, and if it is even, then it will remain unchanged. So let us take example of 2.725 and 2.275. Okay, 2.275. Now again round it off to three significant figures. The digit to be dropped is 5. Preceding digit is even. It will remain unchanged. We will write the answer as 2.72 only. In the next case, round it off to three significant figures. The digit to be dropped is 5. Preceding digit is odd. Increase it by 1. We will write it as 2.28. Okay, we will write it as 2.28. So this is how we round off a digit to any particular number of decimal places or any particular number of significant figures. Next is how arithmetic operations are happened with significant figures. If we are having an arithmetic operation between two numbers, what the result should have, how many decimal places, how many significant figures should be present in the result. Let us see. If we want to add or subtract two numbers, okay, if we are having addition or subtraction of two numbers, then the final number should have as much decimal places as the number with minimum decimal places. Okay, the final result should be reported to the same number of decimal places as that of the original number with minimum number of decimal places. Okay, the final result should be reported as the number having same number of decimal places as the original number having minimum number of decimal places. So if we have 1.2 and we want to add 2.343, add them, what we will get is 3.453. We will getting 3.543. Now how many decimal places are in this number? One decimal place. It is having one decimal place. And how many decimal place in this number? It is having 3 decimal place. Now result should have only that much decimal places as the number with minimum decimal places. Okay, as the number with minimum. So which is having minimum? 1 decimal place. Result should also have 1 decimal place. So the number to be dropped is 4. Round it off to 1 decimal place. Round it off to 1 decimal place. Round it off to 1 decimal place. Okay, the result should have only that much decimal places as the number with minimum decimal places. Now round it off. The digit to be dropped is 4. 4 is less than 5, so preceding digit will remain unchanged. We will write the answer as 3.5. Okay, we will report the result as 3.5. Now let us see what happens in multiplication or division. In multiplication or division, final result should be reported to only that much number of significant figures as the original number with minimum number of significant figures. Okay, so final result should have only that much number of significant figures as the original number with minimum significant figures. Okay, let us take an example. Multiply 1.31 with 1.2. Okay, multiplied. 2 ones are 2, 2 threes are 6, again 2 ones are 2, then 1 ones are 1, 1 threes are 3, 1 ones are 1. Now add it. 2, 6 plus 1, 7, 3 plus 1, 4 and 1. What we will get is 1.472. Okay, what we will get is 1.472. Now tell me how much significant figures? This is having 3 significant figures. Okay, this number is having 2 significant figures. This number is having 2 significant figures. Now result should have how much significant figures? With minimum. So result should also have 2 significant figures. How many significant figures should the result have? It should also have 2 significant figures. So round it off up to 2 significant figures. When we round it off up to 2 significant figures, the digit to be dropped is 7. 7 is greater than 5. Increase the preceding digit by 1. So 1.5 will be the answer we will be reporting. Okay, so correct answer will be 1.5. This is how significant figures are propagated in arithmetic operations, addition, subtraction, multiplication and division. Okay, now let us come to accuracy and precision. What is accuracy and what is precision? Suppose I am having some values, A and B student. Okay, A and B students, they are measuring length of a rod. Let us take length only as we are used it in the whole lecture. So A reported me the result as 1.6 meters. Okay, A reported me the result as 1.6 meters, while B reported me the result as 1.323 meters. Okay, 1.323 meters, and actual length of the rod. Okay, actual length of the rod L is 1.5 meters. Okay, actual length of the rod is 1.5 meters. Now tell me which value is more closer to the accurate value. Which value is more closer to the accurate value? Obviously 1.6 is more closer to the accurate value. So this is more accurate. This is more accurate. Now, which value is more precise? In which value we can measure up to greater depth? We can measure up to many resolution. In this A, we can measure only up to 1 decimal place, 1.6 meters. But B can measure up to 3 decimal place, 1.323 meters. The resolution of the scale, limit of measurement is greater in B. This value is more precise. This is more precise. In this, we can measure up to more limit. So this is more precise value. Limit of scale measurement resolution is greater. So what is accuracy and what is precision? Accuracy tells us the closeness of the measured value to the actual value. Okay, it refers to the closeness of a measurement to the true value. Which value is more accurate, more correct? Any value which will be more closer to the correct value will be more accurate. And precision refers to the resolution limit of the quantity being measured. If I can measure it to 1.1 meters or 1.12 meters, 1.123 meters, so limit of resolution, okay, limit of resolutions tell us accuracy. See, in this case, we can measure only up to 1.1 meters, but in this case we can measure up to 0.001 meters. Okay, so this is more precise. So precision is determined by the least count of the measuring instrument. What is least count? The minimum value what we can measure using that instrument is called its least count. Smaller the least count, greater is a precision. Okay, smaller the least count, greater is a precision. So this is precision and accuracy. Accuracy tells us closeness to the true value, and precision tells us up to what limit of the scale we can measure it. Next comes errors. What is error in a measurement? Whenever we do a measurement, we get some values. Okay, whenever we do a measurement, we get some value. How much, by how much amount this measured value is deviated from the actual value. By how much amount this measured value is deviated from the actual value is determined by errors. So error in a measurement is equal to the difference between the true value and the measured value of that quantity. What is error? Difference between the true value and measured value is called error. There are many types of errors: systematic errors, personal errors, random errors, least count errors. Error can be due to the inaccuracy of the measurement, carelessness of the person which is being measuring, or external environmental conditions are being disturbed. So all these can lead to errors in our measurement. Now random errors are random in size and random in direction also. Either they can induce a positive error or they can induce a negative error. How we can calculate random error between of any measured quantity? Okay, so random errors are totally random. Okay, random errors are totally random. They are random in direction as well as magnitude also. Okay, how can we minimize them? We can minimize them by doing a large number of repetitions. Okay, by repeating the measurement process large number of times, we can reduce this random error. See, if first value is having, suppose this is the actual 1.2 meters length. Once I measured 1.3, then I measured 1.1, then I measured 1.4, then I measured 1.0. So again the difference, the deviation of the actual value, measured value from the actual value is random. Once it can be positive, it can be negative. So if we do large number of repetitions and take their average, then the average will be very, very close to the true value, and that average can be treated as the true value. Okay, so arithmetic mean of all measurements can be taken as true value of that quantity. Suppose we are measuring a quantity A. Suppose we are measuring a quantity A and we do a large number of repetitions and got the result as A1, A2, A3 up till so on AN. Okay, I did repeated the result n times and got the values as A1, A2, A3 and AN. Then the true value, okay, true value can be taken as the arithmetic mean of all the values A bar or A average. This will be equal to A1 plus A2 plus A3 up till so on plus AN divided by N. This arithmetic mean will give me the true value. Okay, this arithmetic mean will give me the true value of my quantity. This will be my true value. Now how to calculate its error? How to calculate its error? Error is the deviation of the measured value from the true value. So what is absolute error? Magnitude. Magnitude of the error. So what is my error? Delta A1 will be equal to A1 minus true value. Measured value minus the true value. This will give me error in first reading. Similarly, delta A2 will give me error in second reading, that is A2 minus A bar. The mod, the magnitude only of these errors is called the absolute errors. So similarly, delta A3 will be equal to A3 minus A bar, and so on we can calculate delta AN, which is equal to AN minus A bar mod. So this is the absolute error in each measurement. Okay, this is the absolute error in each measurement. Now what is the overall absolute error in A? The mean of all the absolute errors. The mean of all the absolute error is called the mean absolute error. So delta A bar will be equal to delta A1 plus delta A2 up till so on plus delta AN divided by N. This will give me the mean absolute error in A. This will give me the mean absolute error in A. Now how we will report the result? Result will be reported as true value. A will be equal to true value plus minus delta A mean. Okay, plus minus delta A mean. If we take absolute value, because these are only absolute only, we will get a positive value only, or we can write this mod or we can not write. It is up to us, but this result will be reported like this. So we have two limits of A. We have two limits of A. A will lie either between A plus delta A or A will lie A minus delta A. So we will get two limits of A. Whenever we will measure A, the value will lie between these two limits. Okay, this is how we report the result, and this is the mean absolute error. Now let's see relative error. Relative error is delta A bar divided by A bar. This will give me relative error. What fraction, okay, what fraction of the true value is my error value? Percentage error. Percentage error will be equal to delta A bar divided by A bar into 100%. This will give me the percentage error. Okay, this will give me the percentage error. Now let's see how errors propagate. Now let's see how errors propagate in combinations. Okay, we measured some quantity A and we measured some quantity B. There will be some error in A, there will be some error in B. Now what will be the overall error in A plus B, A minus B, A into B, A divided by B, A raised to the power n, B raised to the power n? All these are combinations of the quantities. So how errors propagate in combinations? Let us see that. Suppose we have two physical quantities A and B, which are being measured as A plus minus delta A and B plus minus delta B, where delta A and delta B are their absolute errors. Now if we have the first, Z is equal to A plus B, okay, we want Z is a value which is equal to A plus B, then delta Z, what will be the mean absolute error in A? So mean absolute error in Z will be mean absolute error in A plus mean absolute error in B, okay. Mean absolute error in Z will be mean absolute error in A plus mean absolute error in B. Now if Z is equal to A minus B, then also mean absolute error in Z will be equal to mean absolute error in A plus mean absolute error in B. Why we are adding the errors in addition as well as subtraction? Because we always write the answer with maximum possible value of error. We always report error as maximum permissible error. So we have to add both the errors, okay. If we have addition or subtraction of two quantities, the error in that quantity will be addition of their mean absolute errors. Delta Z will be equal to delta A plus delta B. Now third, if we have Z is equal to A into B, okay, if Z is the multiplication of two quantities, then delta Z by Z will be equal to delta A by A plus delta B by B, okay. Relative error in Z is equal to the sum of the relative error in A plus relative error in B, okay. Now in addition and subtraction we have sum of mean absolute errors, but in multiplication and division we have relative error in Z is equal to relative error in A plus relative error in B. Now next is, if we have Z is equal to A by B, then also delta Z by Z will be equal to delta A by A plus delta B by B, okay. If we have division or quotient, then also relative error is the sum of their relative errors. If we have Z is equal to A raised to the power n, so delta Z by Z will be equal to delta Z by Z will be equal to n times delta A by A, okay. If we have A raised to the power n, then relative error in Z will become n times the relative error in A. Now in general we can write, if we have in general, Z is equal to A raised to the power x, B raised to the power y divided by, or let us take A raised to the power m, B raised to the power n, C raised to the power p and D raised to the power q. Then we can write delta Z by Z will be equal to m times delta A by A plus n times delta B by m times delta B by B, what is, sorry, n times delta B by B, what is power of C? P times delta C by C plus what is power of D? Q. So Q will come forward, Q times delta D by D. This is how we will report the result. In general we can write the result like this, okay. So this is how we will report our result. This is a very important equation. So this is all about errors. So this is all about units and dimensions. Quick recap. I hope it was very useful to you and you got the quick revision of the whole chapter in one snapshot, okay. So keep studying, take care, goodbye, keep rocking. Bye bye.